Section 5.3 continued. We've already defined concurrent lines. They are three or more lines that intersect at one point. That one point is called the point of concurrency. Theorem 5.6 states, the perpendicular bisectors of the sides of a triangle are concurrent at a point. We know that that point is called the circumcenter. That point of concurrency is equidistant to the vertices of the triangle. So here I'm given perpendicular bisectors. My perpendicular bisectors in this triangle are AD, BF, and CE. They are concurrent at point G, the circumcenter. Point G, from stated in the theorem, is equidistant to the three vertices. Therefore, GA, GC, and GB are all congruent. If I knew that AG is equal to 3 centimeters, then I would know that GC is 3 centimeters and GB is 3 centimeters. In these diagrams, we have the circumcenter on three different types of triangles. In the acute triangle, the circumcenter occurs in the interior of the triangle. But a segment from the circumcenter to each vertice, we know, would create congruent segments. And that is from Theorem 5.6. In the right triangle, the circumcenter occurs at the midpoint of the hypotenuse. And the segments from that point to the three vertices would create congruent segments. And if we go back and take a look at these two triangles, we know that we are going to create isosceles triangles inside of my triangles. Therefore, if I know angle measures, I can determine many angle measures knowing the isosceles triangle theorem. In the obtuse triangle, again, we have a circumcenter, and segments from the circumcenter to the three vertices would be congruent. Again, creating isosceles triangles. In our first example, we're given the perpendicular bisectors of triangle ABC meet at point D. Point D is the circumcenter of the triangle. And from Theorem 5.6, we know that the circumcenter is equidistant to all three vertices. So the segment DA, DC, and DB are all congruent. I need to find the measure of segment DB. AD is 14. Therefore, DB is 14. And DC is 14. We know that we're given perpendicular bisectors, and DE is a perpendicular bisector of AB. Since AB is 22, the measure of AE and EB is 11. In the next example, the perpendicular bisectors of triangle HIJ meet at point K. Point K is the circumcenter of the triangle. It's given that IJ is 18 and that KJ is equal to 12. From Theorem 5.6, I know that the circumcenter is equidistant to all three vertices. Therefore, KH, KJ, and KI are congruent. I want us to find a length of HK. Since KJ is 12 and HK is congruent to that, HK is 12. They also want us to find the measure of IM. IJ is 18. M is the midpoint. Therefore, IM and MJ are both 9. In this example, we're given K is the circumcenter of the triangle. Therefore, if I found all the perpendicular bisectors of the three segments of the triangle, they would intersect at the point of concurrency, the circumcenter, which is K. They want us to find the measure of AK, KB, AB, and the measure of each angle. From the theorem, we know that the circumcenter is equidistant to all three vertices. Therefore, AK, KB, and KC are all congruent. Therefore, I know that the length of AK is equal to the length of KC, which I know to be 7 centimeters. I know that KB is also congruent to KC. Therefore, it is 7 centimeters. And AB is determined because I know that AK is 7 centimeters and KB is 7 centimeters. Therefore, AB must be the sum of those segments, which is 14 centimeters. As stated on previous slides, when we know this theorem occurs at the circumcenter, we're given isosceles triangles. Therefore, I know that triangle CKB is an isosceles triangle. Therefore, I know that the angles opposite those sides are congruent. Therefore, KCB is 30 degrees. If these two angles are 30 degrees by the triangle sum theorem, I know that the three angles add up to 180. 180 minus 60 leaves me this angle to equal 120 degrees. We're given that this is a right angle. Therefore, angle KCK is complementary to this 30-degree angle, which leaves us 60 degrees. I know that triangle AKC is isosceles. Therefore, by the isosceles triangle theorem, if this angle is 60, angle A is 60. And either by the triangle sum theorem or supplementary angles, I know that this angle has to be 60 degrees. Theorem 5.7. The bisectors of the angles of a triangle are concurrent at a point equidistant to the side of the angle. Recall that the point of concurrence for the angle bisectors is called the incenter. Here we have diagrammed an incenter. That is the point of concurrency to the angle bisectors of this triangle. By the definition of equidistant, that means that these segments are congruent. And by the definition of equidistant, it means a segment from the point to the line that is perpendicular from the point to the line. So the incenter is the point of concurrency, but every segment from that point must be perpendicular to the sides of the triangle. And when that occurs, that's going to tell me that those three segments are congruent. For our first example, the angle bisectors of triangle ABC meet at point D. D is the incenter. They want us to find the measure of DE. Point D is the incenter of my triangle. That is the point of concurrency for the angle bisectors of triangle ABC. In the diagram, we're given that the length of FD is 17. Therefore, all segments that are equidistant from point D to the sides of the triangle are congruent. That is from theorem 5.7. And those segments that are equidistant are the perpendicular segments from point D, the incenter. That would be DF, DE, and DG. Therefore, DE is congruent to DF. Therefore, DE is 17. The next example. The angle bisectors of triangle ABC meet at point P. P is the incenter and the point of concurrency for the angle bisectors of triangle ABC. And by theorem 5.7, that point being equidistant to the sides of the triangle are congruent. We're given that PR is 3. We're given that PC is 5. But we're asked to find the length for QP. That is one of the three segments that are congruent. Therefore, QP is equal to 3. Median of a triangle is a segment from the vertex of the triangle to the midpoint of the opposite side. Here we have a diagram. We have a segment from vertex A. It is to the midpoint of segment BC, which is the opposite side of the triangle. Theorem 5.8. The medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex. to the midpoint of the opposite side. Here, we're given triangle ABC. We have medians AM, BN, and LC. They are concurrent at point P. Point P is known as the centroid, the point of concurrence for the medians. Here, the centroid is defined in theorem 5.8 to be segment AP is 2/3 of the entire median. Here, PM is therefore 1/3 of the entire median. That tells me that from each vertex to the centroid is 2/3 of the entire length of the median. Therefore, AP is 2/3 AM, BP is 2/3 the entire median, which is BN, and CP is 2/3 the entire median, CL. And if each of these is true, then that would tell me that PN is 1/3 of the entire length of the segment, BN, and PL is 1/3 the length of the entire median, CL. In this example, we're given the triangle ABC has a centroid at point P, and we know that AM is 14. AM is 14, the entire length of the median. We want to find AP and PM. From theorem 5.8, we know that from the vertex to the centroid is 2/3 the entire median. Therefore, AP is equal to 2/3 AM. Now I just substitute in. AP is equal to 2/3 the length of AM, which is given to be 14. Therefore, the length of AP is 28/3. The length of PM from the centroid to the midpoint is 1/3 the entire median, which is AM. So now I just substitute 1/3 times AM, which is given to be 14, and that would give me 14/3. To verify that, all I need to do is add these two lengths together, 28/3 plus 14/3. When I combine those, I have a common denominator already. That's going to give me 42/3. And when I simplify that, that's going to give me 14. And that is the length of AM. Therefore, that verifies this problem and theorem 5.8. As previously defined, the altitude of a triangle is a perpendicular segment from the vertex of the triangle to the opposite side. And here in the diagram, we have triangle A, B, C, and we have altitude AD. It is starting at the vertex, point A, and is perpendicular to the opposite side of A, and that would be segment BC. Theorem 5.9 states, the lines that contain the altitude of a triangle are concurrent. In this diagram, again, we have triangle ABC. I have three altitudes. The altitudes coming from point A, B, and C intersect at point P, and at that point is called the point of concurrency, and in the altitude, that is called the orthocenter. That's the point of concurrency for the altitudes of a triangle. The last two definitions of the section. On the top, we have circumscribed about the triangle. That's when the circle intersects the vertices of the triangle. In other words, the circle is on the exterior. The center of the circle is determined by the circumcenter. Therefore, if I found the perpendicular bisectors of this triangle, the circumcenter, which is the point of concurrency for the perpendicular bisectors, would determine the center of the circle. Inscribed circle. Each side of the triangle is tangent to a point on the circle. In other words, the circle is on the interior. The center of the circle is determined by the incenter. Recall, the incenter is the point of concurrency for the angle bisectors. Also, tangent means a segment that intersects a point on a curve. So each segment of the triangle, in reality, only intersects a point on the circle.